All right, so let's do some explaining from the sticky tape lab that we completed today. This is going to be a great jumping point to give us an explanation of the internal structure of our atom. And we're going to start with how we came to understand the initial structure of the atom back in the late 1800s. So we'll ask this first question: why do the tapes attract and repel? We know that they do attract and they do repel, but why is it that they do that? And we have this little chart that we put up on the board, and you had on your whiteboards that told you what it repels and what attracts. And hopefully from this chart we understood that the top and bottom tapes were oppositely charged. That's why the two of them repelled. And then everything else kind of attracted to them, which seemed odd, because things like the aluminum foil not only attracted to the positively charged piece of tape, but also to the negatively charged piece of tape. And it seems as though if it would attract to one, it should repel from the other. So we need to discuss what's going on there. We're going to assume that each atom contains both positive and negative charges that normally cancel each other out. And this is a pretty good assumption. This is the valid assumption that we had in the late 1800s. And in fact, we had a model of the atom. We thought the atom looked kind of like this. So that a red cloud, a spherical cloud of some type of positive charge, and then these blue dots scattered throughout this cloud. And these blue dots were known as the negative charges, or the electrons. This particular model is actually called the plum pudding model. I have no idea what plum pudding is, so let's call it like the chocolate chip cookie model, okay? So if you think about like a three-dimensional chocolate chip spherical cookie, like a chocolate chip cookie ball, that'd be awesome. And then having the chocolate chips being the electrons. So they're kind of just scattered throughout the cookie being the positive entity, and that was our atom. That's what we thought the atom was. But to explain the source of these charges, where do they come from, and what do they do, and how do they move, we need to kind of expand our model of the atom. And we got to have a little bit more internal structure. So that leads us to this guy, in that picture that I showed it before with the plum pudding, or maybe the chocolate chip ball pudding, is based upon J.J. Thomson's discoveries. And this is the guy that discovered the electron. We'll look at some of his experiments that led him to do this. And he proposed the following. He said that in solids, only the negative charges are free to move. The positive charges are fixed. They don't move around a whole lot. But the negative charges can move back and forth a little bit. And he also said that these charges are much, much smaller than the atom on a whole. They have charge. They're identifiable. But overall, they're very, very tiny. And now he didn't exactly know how tiny they were. It took a later experiment by a gentleman by the name of Millikan to figure that out. But he did know that they were very, very tiny. So he comes up with that plum pudding model that we expressed in the previous slide. So again, the positive cores are represented by bowls. So if we can maybe make a picture here of his plum pudding model, we could say that the circle here is like the bowl. And we're just going to refer to it as plum pudding. You're just going to have to live with that. So the bowl itself, this bowl and everything kind of like the space around it, is the positive portion of the atom. And then that makes the pudding, or the plums rather, the negatives. So they're like little spheres inside of the pudding. Here's the plums. I guess plums are purple, but now they're going to be red. There we go. So that's our, like I said, our plum pudding model. So the positive cores are represented by bowls of pudding, which attract the negative electrons represented by plums. So just as this atom sits as it is, it's pretty happy. Now, what happens if we bring along a second atom? And maybe this atom has a little bit stronger of an attraction for those plums. Well, what Thomson notices is that these electrons, they can move, and you guys notice this too with your tape. You notice that when you rip the tape apart, you now had a charged entity, one being a positively charged and the other one being a negatively charged. And the only reason that could have happened was if we actually had a transition of these electrons. And that's what happens. We have some atoms that have a stronger affinity. They want to scoop up, they want to attract the electrons more. So their bowls, as I've drawn with these green circles, are more are stronger, more attractive to the electrons. So the electrons jump over to those particular atoms. So let's look at our model then. This is going to be a picture of our tape before we stuck them together. Okay, before adhesion. Okay, and as we're going to see here, the top tape, that's going to be the one on the top, and the bottom tape is the one on the bottom. They're totally identical. They're just two pieces of tape. They're different pieces of tape, but for all intents and purposes, they're identical. Now, we define the top one as being positive. Right now, it's not, but it will be shortly. And we define the bottom one as negative. But again, at this point, before they're adhered together, as you just take them off the tape roll, they're both identical. All right, now let's put them into contact and see what actually happens when they contact each other. All right, when they're in contact now, so they're pressed together, we notice that there's kind of a flow of electrons. You know, if you noticed from the previous model, there were 3 electrons in each circle, and now we actually have 2 electrons on the top and 4 electrons on the bottom. Okay, again, the top one being positive, it's losing the electrons. It's kind of weird to think if it's losing something, it's becoming positive. But think about that. If it's losing electrons, it's losing the negative things. Those little black spheres, each one of these black spheres is negative. So if it's losing negative, it becomes more positive. And the bottom one is then negative. So this is in contact before you're ripping them apart. All right, now let's separate them. Okay, we rip them apart real quick. And what we notice is that the electrons stay on the bottom piece of tape. Okay, and then what happened? Well, you put the 2 pieces of tape together, and they attracted each other. Okay, after we did it the second time, right? After we did it the revised time. So now we have a piece of tape that's positively charged, and we've got a piece of tape that's negatively charged. So what do we know? We know that electrons now can transfer via material contact, just by placing them together. So we didn't have to rip these things apart for the electrons to transfer from the top piece of tape to the bottom. By the way, we're defining the top as being positive and the bottom as being negative. You may have asked the question, well, how do we know what's positive and what's negative? We don't know, and to be honest, it doesn't matter. All we know is that one's positive and one's negative, and that's good enough for right now. So when the electrons transfer via material contact, this creates an imbalance of charges. Somebody had said the other day that there's no charge on the material. That's not true. There's always charge. It's just usually the charges balance out on materials. So what we did is we created an imbalance of charges, and this creates an attraction between the 2 objects. We put the top and the bottom pieces of tape together, and they attract each other. And it's important to note that the total number of electrons really never ever changes. It's just that their location does. So, here's your example. You've got 2 pieces of tape that are separated on the left. You put them together, and then they repel each other. And why is that? Well, the electrons. Now these are both positively charged, as you can see by the plus signs. So the total number of electrons when we separate the tape, it doesn't matter how we did it. If we did it like we did it the first time when we kind of goofed up, or the second time, the total number of electrons doesn't change. It's just that they transfer their locations. They change their locations. This actually has kind of real-world applications. This is the Northern Lights, as they're called, or their scientific name is the Aurora Borealis, if you're here in the northern hemisphere. And what happens is electrons actually, they bombard. They actually transfer from space to nitrogen and oxygen molecules in our atmosphere. So you get a transfer of electrons. And when this happens at such high rates of speed and such high frequencies, that causes the nitrogen atoms to become excited. And they actually give off colors when they become excited. I don't know. I just kind of jump for joy or smile or something. I don't give off colors. Now, here's the interesting part about this whole app. It's not the whole tape thing, because I think that's understandable. It's that it doesn't matter which piece of tape we put up to the neutral foil or to the paper. There's the same effect every single time, right? It's the attraction. It attracts every single time. And it should be that, at least intuitively, you should think that if it's attracting to the negative, it should repel from the positive. But that doesn't happen. So let's think about this. Here's the neutral foil. This is the picture of the foil. And each one of these circles is an aluminum atom with the electrons dispersed throughout. Now, let's bring the T-tape, the top tape, towards the foil. Check this out. Here's what happened. The electrons congregate closest to the positive. So this is our positive tape right here. That's our positive tape. And look at the electron flow. And as you look at the atoms on the right, oh, those poor atoms, they're almost devoid of electrons. All of the electrons are leaving. They're saying, oh, we're going this way. We're going this way. Remember, the charge on the electron is negative and opposites attract. And so all the electrons are pulling this way, this way, this way, this way. And so that's why we get attraction between the foil and the positive tape. Oh, there we go. And what's really cool is metals do a great job of allowing their electrons to transfer from one atom to another. It's something called conductivity. We'll learn that a little later. Now, what about the B tape? How does that look? Remember the B tape? Oops, I gotta go back. How would the B tape look? Okay, the B tape was negative, right? Okay, so we have all of the aluminum atoms. There's one, and they're connected, right? They're supposed to be the same size, so just trust me that they are. And then there's electrons in each one of them. Okay, I'm doing this kind of quick. Okay, electrons, 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 electrons. And then we bring the B tape up. So we bring the negative up to it. So we bring the negative tape up to the aluminum foil. And what happens with those electrons? What do they start doing? Well, we noticed that the foil was still attracted to the tape. Well, the electrons actually go away. They don't like being close to the negatively charged tape. So the electrons actually move in this direction. They start flowing away from the B tape. Away, 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 away. And pretty soon we're going to have aluminum atoms. I'm not creating any. They were there. I just hadn't drawn them before. We're going to have aluminum atoms that have few, if any, electrons inside of them. Probably just few electrons inside of them. So what's left? Well, all that's left is the positive core. So the electrons are still there. They're just now on this side of the aluminum foil, leaving this side to be negative. And now this side of the aluminum foil is positive. And oh, check it out, positive, negative. There's your attraction. There's your attraction. So that's why the aluminum foil attracted to both positive and the negative tape. Now, one thing we may or may not have observed is that the attraction between both B and T for the aluminum foil is supposed to be greater than for the paper. And it's hard to observe. You really have to look close, but it is the case. Here's why. In metals, electrons can be compelled. They can be driven to move from one core to another, so from one atom to another, by the application of an external electric field. So our electric field in this case was the tape. It was electrified. Okay? This is the components of a good conductor. This is what conduction is. This is why copper wire is used in walls to run electricity. It's because the electrons from the metals can be coerced, can be compelled to move from one to another real easily. And the flow of electrons is nothing more than electricity. The pushing of the electrons that we showed in the previous slide is the concept of polarization. So whenever you push electrons to one side of an atom, that's the idea of polarization. Okay? You're forcing one side of the atom to be more negative than the other, or one side of a molecule to be more negative than the other, or one side of a piece of metal to be more negative than the other. Now, the paper isn't metal. We know this. So with things that are not metals, the electrons are not as willing to kind of travel across one another. The electrons are going to stay within the atom. So if you think about all the little paper atoms, whatever those are, in the electrons that are inside of them, all of the electrons are kind of compelled to stay within each atom. So you'll notice that, see, the electrons in this case, they're still pulling towards the plus sign, but notice they're staying inside of the circle. So there's less pronounced polarization. The effect of polarization in an insulator is less pronounced. Okay? All right, now we know this flow of electrons idea. That's going to help us understand conductivity. That's going to help us understand bonding.